Thanks again, Dan, for the very clear presentation, and thanks to Ernie already for an excellent suggestion of a bathroom break. So our second presentation here will be by Ernie Lewis, who will be talking about the MAGIC program. He's the lead scientist of the MAGIC program at the Brookhaven National Laboratory. He's an atmospheric scientist in the Environmental and Climate Sciences Department. Did his graduate training at UT Austin, and is interested in a broad range of things, including measurement of marine clouds, aerosols, and radiation properties, biomass burning aerosols, air-sea exchanges, including sea salt and sea spray aerosols, among many other things. So thanks very much for agreeing to come on, Ernie, and we look forward to hearing about the program.
Thank you very much. Can you hear me okay?
Yes.
Okay, so thank you for the invitation for CLIVAR, Kristen and Chris. Dan, that was an excellent talk. As I pointed out at the break, that's a very tough act to follow, so I'll do the best I can. I was the PI on MAGIC, which is the Marine Arm GPCI investigation of clouds. I'll get into all that in a bit. A one-page summary in case you have to go. MAGIC was a field campaign that was run by the ARM project. It's actually now the ARM Atmospheric Radiation Measurement Climate Research Facility. It's a part of DOE. It's a user facility, but it's just known as ARM, and that's what I'll refer to it as. The goal was to study the stratocumulus to cumulus transition that occurs as you're going from Los Angeles to Hawaii. You have a stratocumulus deck right off the coast, and as you go further out near Hawaii, it's puffy trade-wind cumulus, and that transition is not well represented in models. The objectives were to measure the properties of everything we can: clouds and precipitation, aerosols, radiation, atmospheric structure. We also had sea surface temperature, and use those to improve the representation of this transition in climate models. We deployed the second ARM mobile facility, and Dan had done a very good job describing that. And that's the set of radars and instruments. And we put that on the Horizon Line's cargo container Spirit. So we put it on a commercial cargo vessel, and that was challenging, but turned out to work very well. And I'll show pictures of that. We did repeated transects LA to Hawaii over a period of a year. There was unfortunately a break in the middle. If you're a commercial ship, the Coast Guard says twice every 5 years you have to go into dry dock. And we happened to be lucky and pick one of the years they were going in, but we still had 20 round trips and almost 200 days at sea. So from what I gather, this is the largest radar study at sea that's been done. We have a great data set. It's, as Dan mentioned, it's freely available to all. It's not my data. People come up and ask if they can work on it, and my thought is I want everybody working on MAGIC. We try to work with you. Certainly contact me, because there's a lot of information that can't be put right in the archive as far as things that might have happened or conditions under which data we're taking and so forth. But anyway, that's your one-page summary. If you have to go, I'll try to fill in some blanks now. I was a principal investigator. There's a number of co-investigators. This doesn't mean what it might in some other field campaigns. These are basically people that are interested in the data, but ARM, being a user facility, takes proposals, and Dan was awarded the one for Antarctica. I was awarded the one for MAGIC, and then they deploy the instruments, take the measurements, put the data in the archive, and it's not a program that I run in any sense. So the co-investigators don't have a formal role, at least in MAGIC they didn't, but they're typically people that are very interested in the data, and most of them have worked on those data. Okay, the acronym, first of all, that's a magic wand. It's and a cloud on top. Some people, unbeknownst to me, thought it referred to some other instrument, which I never crossed my mind. ARM is the Atmospheric Radiation Measurement Climate Research Facility. GPCI is the GSCSS Specific Cross-Section Intercomparison. GCSS is Global System, or GWEX Cloud System Studies. And GWEX is the Global Earth and Water Cycle Experiment. And from then meaning when the acronym was made till now, GCSS has now changed to Global Atmospheric System Studies. GWEX has changed its name, and GPCI is no longer operational. So it's easiest just to refer to it as MAGIC, and that's what I will do. My understanding is back in the early 90s that GWEX or GCSS picked about half a dozen regions around the world, transects, that represented different cloud regimes or transitions between them, and that made comparisons along those transects easy because with a one-directional spatial on the transect and vertical, you can easily show model results in a two-dimensional pattern. And GPCI was a transect that they used, and I'll show a picture of that in a little bit, to study this transition. And so the motivation is that clouds play a very critical role, as we know, and marine boundary layer clouds are especially important, and it's very difficult to represent these in models. Models have had big discrepancies, as I'll get into, and this is one of the regions where those discrepancies. So this is the magic transect. The GPCI transect is a solid line here. The magic transect goes from Los Angeles to Hawaii. This is the false color plot is the June, July, August low-level cloud cover. It goes from about, well, very low near Hawaii, where it's cumulus, to very high in this big stratocumulus deck. So just similar to GPCI, we're going right through that deck back and forth. This was adopted from João Teixeira's paper in Journal of Climate, which had 23 climate models investigate this transect. So it's about 4,100 miles from Los Angeles to Hawaii. It's very near the GPCI transect, so this worked very well. And this was part of the motivation, that the different models, this is 23 different models showing a mean in the white, I believe, and a standard deviation in the low gray, and then the range in the darker gray for total cloud cover and total liquid water path. And this is the latitude, so the northern part, or the eastern part near Los Angeles, is around here, and then Hawaii is around here. Here. Hawaii is at about 20, just over 20. So this goes on further. The transect goes on to the equator a bit past. But the point is, you can see there are huge discrepancies among the different models here. So this is not well known, and something like total liquid water path, through the stratocumulus region, estimates range from 20 or so grams per meter cubed up to over 200. So this is not a good state of affairs, and even the standard deviation ranges from 25 or so up to 150, and we need to do better. And part of the reason we don't know that is it's very difficult to take accurate measurements at sea. We can do satellites, but stuff that happens in the boundary layer, which is a kilometer or two high, it's very hard to get that data from satellites. So MAGIC was an attempt to get some data on this. So scientific objectives were to improve the representation of this transition in climate models and to produce the observed statistics over a period of a year. So we didn't get quite a year, but we got a good portion of it. This is just a picture showing this. So it is a true marine deployment. There's not island effects like you have in other places where you're on an island. It's easy to park radars and instruments there, but you're concerned about what perturbations you have. So we went back and forth here, and it, as you can see, goes quite a bit into the ocean. So approach, we were trying to measure everything, as said. We were trying to measure properties of clouds and precipitation with various instruments, measure atmospheric and oceanic conditions. We had sea surface temperature. We had basic meteorology. We had the same aerosol suite Dan was talking about, where we had a whole set of aerosol measurements, and then radiometers of various sorts, and I'll have pictures and slides of all these later. Model intercomparisons that we're interested in is GPCI, which is no longer an active working group, but can be resurrected. Eclipse, which is a European Union cloud intercomparison, and GCILS, and if you remember back on that, it's a large eddy simulation and single column model intercomparison. And there were several points along that GPCI transect that were very near some of our points where they would do the LES and single column models on those points. So a little bit about ARM. Dan talked about it some. It's a user facility of the U.S. Department of Energy. It manages 3 fixed sites, 3 mobile facilities now, an aircraft facility, and a data archive. It sponsors and operates field programs around the world. This is an older slide, but I put it together for a previous talk showing some of the locations, the fixed sites, North Slope of Alaska, the Southern Great Plains site. There used to be one in the tropical West Pacific, but now I believe that's in ENA, which is Eastern North Atlantic, which is the Azores. Mobile facilities, there's Mobile Facility 1, and then starting in, I think, 2007 or 8, there's a second mobile facility, maybe it's later 9, and the solid white, or the white rectangles show the different locations as of a couple years ago for the AMF2 to AMF deployments, and then upcoming shows some of these, and that doesn't even show Dan's because I'd made this before that. But you can see it's trying to cover different climatic regions of the globe and for extended deployments. I have here, it consists of 3 20-foot containers. That was on Magic because we were limited by ship space, but in our Antarctica, places where there's bare ground and lots of room, there's up to a half a dozen, I believe, containers they can store spare parts and so forth. This is a radar sea-tainer. Call them a sea-tainer because they can go on ships. This was designed for marine employments, and these are basically the shipping container that cargo containers like the Spirit, which is one we were on, use. This is the aerosol sea-tainer, the aerosol van with the stack. They put railings up there so you can get up and put other instruments on top. And there's other modules that can go, so you don't have to have everything just in the vans. And this is a LiDAR. There are several other modules that were run independently. So Magic was quite a bit of a different field campaign. We were on this ship. This is almost 300 meters long. This is Horizon Lines, which has since gone out of business and been bought up by, it split and it was bought by 2 competitors. But they were tremendously enthusiastic and supportive and hospitable. They let us use the ship for a year, let 2 technicians live on there, let us put our instruments on there, and that made it all happen. So we're very grateful for them. So it's a very nice ship in a lot of ways for what we were trying to do. Everything was done up by the bridge, on the bridge deck. The stacks are back here about 100, 150 meters back, and then the ship usually steams at on the way to Hawaii over 20 knots and on the way back about 16. So unless there's a very severe tailwind, we don't have any contamination from the stacks, and that's very nice. This is also right up by all the living quarters, so marine or balloon launches, radiosondes are very convenient. We tried them originally from the back of the ship when we explored this, and that's quite a haul several times every day, plus dangerous conditions. So this turned out to be tremendously wonderful for a platform for a number of reasons. It's a 30-meter wide. It's got a maximum speed of about 11 meters a second. It was built in 1980, which is a real advantage for us because the newer ships, if you've ever seen a new cargo ship, have absolutely no spare space whatsoever. It's just a huge box container. And this had some deck space that was unused and unsellable for revenue, so they were very gracious to let us put our instruments on those. It's got an FEU, or 40-foot equivalent capacity, of 1218. FEU is the back of a semi-truck. It's a 40-foot container. We had on Magic, the AMF2 is 20-foot containers. So this can carry 1,200 40-foot containers every week back and forth to Hawaii. The round trip is every 2 weeks. It goes over there in 4.5 days. They have a lot of perishables, refrigerated units for medicines and food, a day to turn around, and at 6.5 days to come back because it's mostly empties, and they want to keep it to a 2-week schedule. So 1 day in Hawaii, 2 days in Los Angeles, and this gives a 2-week schedule. We made about 20 round trips through about 200 days at sea between September of 2012 and October 2013. Like I said, this is a cargo container. This is one of the FEU's 40-foot equivalent units. You can see a semi down here. The scale of this is hard to grasp unless you're there. This is what loads the ship, and they can load and unload this ship in a matter of hours with several of these cranes working. It's incredibly impressive. This is the Spirit. This is the bridge house. We had a meteorological mast I'll talk about up here, and other instruments along the deck. It's hard to get pictures also of this because of the scale. This is from the shore. You can see this is the mast again. This is the radars on one of the units. We had another aerosol unit, or an operations unit right here. You can see a radiometer on top and the rails, and then we had another van on the other side over here. And these are the stands for the cargo containers. 2 technicians lived on board the whole time. There were 4 that rotated out. They were incredibly great. They really cared about the data. They went above and beyond. They were wonderful people, and it was really nice to have them being who they were, because I have good faith in the data quality. They got the best that could be done. So that's why I say ARM's different. I was on the ship. There were some science writers on the ship. Peter Kalmus went once. Mike Jensen. Mike Reynolds was on a lot of times, several times with me. Mike was instrumental in getting this done. But this is something that for a year-long deployment, you you can't have scientists typically do. They just can't afford that kind of time, especially from a university for grad students and so forth. But ARM has technicians who are highly trained and can be very good to run the instruments. Let's see, I have a few slides here I tried to do just to be comprehensive. I'm not going to go over it, but these are archived so you can look later. There's a lot of challenges, as you can imagine, for doing a marine deployment. This was the first true marine deployment ARM had done, and there were a lot of technical difficulties and other difficulties to overcome, and they did a wonderful job. Nikki Hickman and her team out of Argonne, Mike Ritchie, and the others were just great. This involved getting helium to the ship on time, to getting supplies that needed to be done. They did a wonderful job on that. So there's challenges of marine deployment. I won't go over. There's requirements for a platform. You need, a shipping company that will let you put technicians on there and instruments on there. You need a good location on the ship that you can see the sky for radiometers and radars without getting, metal things in the way, that you don't want the stacks blowing soot over your aerosol instruments, and just general concerns of, you have to change a ship sometime, and they were very good about welding stuff on the deck, cutting stuff off the deck, depending on the ports the ship is going to, whether they'll have good supplies. So there's just a lot of concerns with the shipboard deployment. There's also things that are very important for the data ship motion. The ship, one, is not in the same place, so getting your radiometers corrected for solar angle and so forth requires some extra work. Ship is rocking back and forth, and if you're trying to do Doppler or vertical motions or vertical pointing instruments, and the ship is pointing in different, the vertical is pointing in different directions, that can be a challenge. You get screening by superstructures, you get flow-induced perturbations. Trying to find the actual wind speed when you're on a ship can be a challenge. It's generally a metal ship, so in the sun it's going to possibly heat up more than what the atmosphere nearby would be. You get reflection, screening by superstructures. So there's a lot of things to overcome, but we did our best. I think they did a good job doing that. So getting on with the deployment, Magic had 3 radars, had a zenith pointing, so this is a stable table and a W-band radar. So it corrected so that the ship was, or the radar was pointing not vertical, but toward the zenith, and it was good to within, I saw the stats once, about a half a degree for the whole deployment. That was very good. The radar wind profiler, and then there's a vertical pointing Ka band. That was too big to get a stable motion platform, so that rocked with the ship. But it was a very big ship, so generally ship motion was within a few degrees. There's 2 things. There's the actual motion rocking back and forth, and then because of the way the ship is loaded and the fuel, it might be offset from vertical by 3 degrees and then up to 3 or 4 degrees, and then rotate or oscillate around that to about a degree either way. So those all required corrections if you're trying to do Doppler, for instance. Other instruments for cloud and precipitation, we had dysdrometers on the ship. There was a ceilometer. We had a 2-channel and a 3-channel microwave radiometer. 2 different LIDARs. Unfortunately, the LIDARs kept breaking, and it was one of these things that the technicians would go, well, we've never seen this. It would be a diode or something just totally independent of the deployment. But we did get some radar data. There's a total sky imager. This is a video camera looking down over a dome here that gets pictures of the entire sky every 30 seconds. Had a CML sun photometer in cloud mode, so it wasn't doing all the scans, which is very hard when you get a moving platform, but every 15 minutes it would pop up and just look vertically, and that would allow us, with certain assumptions and other measurements, to get cloud liquid water path, effective radius, and so forth. This is just a graph from Jalizou at McGill, who's written a paper on this already, of the precipitation during Magic. Most of the graphs we try to do them this way: Los Angeles on your right, Hawaii on the left, like it would look on a map. Makes it a little easier to visualize. And you can see this is sorted by drizzle and virga, and through the stratocumulus deck you get a lot of both, and then down toward Hawaii you get much less precipitation. This is the fractional occurrence, and this is for the entire deployment. Meteorological mast, this is looking from the front of the ship, and you can see the mast is right up. It's not this crossbar, it's the one right up here, with the anemometers on each side, so depending on which side the wind comes from, you would pick and hopefully get a clear view of that. Temperature RH sensor there, optical rain gauge. We had a seabird on top, and another rain gauge here. Precipitation was extremely difficult on this ship to measure, partly because it's very light and partly because you've got a lot of superstructure around and so forth. sometimes have riders along. This was one time where one of the mates caught me and said, your seabird's about to fall off, because this was flopping around all over. And I came out and looked, and there was this guy sitting here, and the wind was directly from his left coming across, so he was providing probably causing a vortex behind it that was just captured right here, and this thing was flopping all over. Now, fortunately, we had one on the other side, which is the one we would be taking anyway, but occasionally you get logistical influences like that. Radiation measurements, we had 2 portable radiation packages. I won't go into all the detail, but it'll be here, a PSP, a PIR, and an SPN. One of these on each side of the ship, so if one side was in the shade from the mast, we could use the other. And we had one FRSR, which is a fast rotating band shadow radiometer, to give aerosol optical depths at 4 different wavelengths there. Additional radiometric instruments, like I mentioned, the CML sun photometer in cloud mode, microtop sun photometer measurements on some leg we got from Brett Holman and Sasha Smirnov at NASA, and they let us use that. That was great. Sea surface temperature measure with ISAR, which is Mike Reynolds and Peter Manette's, actually it belongs to Peter Manette's instrument from Miami, to give sea surface temperature, and there was an ARM instrument to give sea surface temperature. A solar array spectrometer and a solar spectral flux radiometer was borrowed from NASA. They put that on for some of that, and that's been very good to compare these different ones. Surface fluxes, these are, I'll just try to briefly touch on some of the data that we've collected. So we had surface fluxes, I'll leave this here, but trying to get surface energy fluxes, we couldn't do eddy correlation. It's a moving ship, they're not going to stop for us, they've got a timetable, but it was a bulk aerodynamic method. And we think that's pretty good. We got shortwave and longwave radiation from the radiometers, sensible and latent heat, and then precipitation. And Mike Reynolds has done a real nice data set of all that with some README files to explain that. This is just a little bit of a graph I did for something on one of the legs I forgot to mention. Each round trip is called the leg. So leg 15A would be A meaning on the way to Hawaii and B being on the way back. And this is our leg 15, which would have been in July or August of 2013. And you can see the sensible heat here in watts per meter squared varies up to maybe 20. The long wave up and down pretty much cancel, so the net is 40 or 50. This is the solar. The short wave down during the day goes down to about 1,000 or more. And then the latent heat is somewhere there around 100 or so. And then you get your net flux, which is the sum of all these. And there's issues with that because a day can be shorter or longer. The clock day, you're moving toward the sun. You're moving as the day goes on. So, in a 24-hour period, you're starting and stopping at a different location. So it's hard to take an average. And plus, for a 4.5 day trip to Hawaii, most of the time we got 5 daytimes and only 4 night times. So be careful with statistics. You can't just average over the trip, or you're going to be biased toward more daytime and thus more shortwave downward. This is for another leg, 07A, which is in the winter season. You can see the solar is not nearly as great here. Radio sun launches, I think this is one of the best data sets. We did 4 radio sun launches per day during the deployment. For one round trip in July, for a 2-week period there, we did 8 radio sun launches a day. We were going to do another one in January, but the ship had to come in a dry dock a little earlier than expected, so we didn't get a summer-winter comparison. But out of 695 attempts, there were 565 successful, which is an 80% success rate. And if you were out there and saw the conditions that was under, that's nothing short of remarkable. I would ask the technicians to do a log every time, and this is the relative wind speed, and you can see they're attempting, radio sun launches at 24. They got a successful one at more than 24 meters a second. Up to 15, the sounding terminated. The Saund hit a container. 11. So this is truly remarkable, and this shows some of the things. You're out there at night. We're launching off the lower deck. If you've ever launched a Saund, you've probably never seen a weather balloon in that kind of shape. Multiple people. We're trying to use nets when the winds are from different directions. And typical situation is this, where you've got this wall of containers there. The ship is moving toward the screen at 11 meters a second, and you're trying to launch this way with, just very little lead time before you come up to this massive wall of containers. But we got over 500 successful ones, and that's, I think, a fabulous data set. This is a compilation of the boundary layer height in the cold season and warm season, the mean. But you can see pretty uniformly you start at about 1 kilometer near California and increase to about 2 kilometers near Hawaii for your boundary layer height there. A couple Saund just profiles here. This is in July of 2013, July 8th, and the RH you can see starts at about, it's in the red, 80%, goes up to about 100 there, and then within about 50 or 60 meters drops down to about 20. So the inversions are very high, and the transition from the top of the boundary layer to the free troposphere is quite extreme there. Temperature drops off to cloud base, and then you drop from about 10, or increase from about 10 degrees to almost 20 degrees there, again between 905 and 895 millibars or something. In 50 or 100 meters, you get these extreme transitions. This is another one. This is further out. The previous one was where we had the stratocumulus dec. This is where we have the decoupled boundary layer closer to Hawaii. The atmosphere is fairly well mixed with some perturbations here, but you're about 80% RH, and then you drop off, and you can see the little blip. I believe this is where you have your decoupling there. So not as sharp of an inversion. Aerosol measurements. This is the aerosol van. There's other instruments on top. There's drometers, communications, and so forth. Inside is just racks of aerosol instruments. And again, I won't go over all of them, but we had a CPC, the condensation nucleus counter. This is one of the best ones we had for most of the deployment, not all, the ultra-high sensitivity aerosol spectrometer. It detects optically, counts particle by particle. Dry and humidified nephelometer is a PSAP for absorbing aerosol. It's a filter-based, and then HDMA. We also had some aerosol sampling on there for individual particle composition and for ice nuclei and RNA that Altamont did. Where I'm in time. Okay, I got a couple minutes. I'll go quickly. Just some of the aerosol data. Each color is a different leg. Again, this is Los Angeles to Hawaii. And you can see the variability leg to leg in the number concentration, but they're quite low. This is for the UHSAS, 55 nanometers diameter or above. And on some legs, you're getting 30 or 40 particles per cc, and even at the extreme, you're getting 150. So this is pretty clean air most of the time. This is the average particle radius, and again, a lot of variability just from one leg to the next, and that hasn't all been figured out yet as to why, or at least by me. This is plotting the number with optical diameter greater than 55 or 60 nanometers to the total CN concentration less than 10, and they correlated very well, but you'd have different slopes on different legs, and they were almost linear, but with different slopes, again, depending on leg, and that was interesting. Size distributions is a very rich data set here. This is a nephelometer. And the two jumps are when you would do a 1 micrometer and 10 micrometer cut. So you can see that the at low, when you have the 1 micrometer cut and just have sub-micrometer diameter particles, your aerosol extinction is of the order of, or scattering is of the order of 10 inverse megameters. But when you include all particles, you're getting up to 20, or in some cases 30, or maybe even more, which shows that the particles greater than 1 micrometer diameter, which are extremely few in number, probably less than 1 per cc, provide more than half of the light scattering, and that's typical in marine aerosol. This is a slide from Paul DeMott of showing some of the magic ice nucleation data compared to other data sets that he has, and he just got a PNAS paper out of this recently. Other data, ECMWF and Micah Algren have given forecast data for the whole rectangle, including this track. Those are all in the ARM archive. What I try to do is develop an instrument status table. These are all the instruments, and just a code for what's usable, what's good, what's questionable. These aren't totally up to date, but I asked the technicians to keep this as a running commentary, so you know, okay, if we're going to pick a magic leg to work on, and we've tried to do that, pick up golden legs and say, okay, let's everybody analyze this leg or that leg. You know, you don't want to pick something like this. You'd want to pick something like this, at least for up here, where you've got the vast majority of the instruments working. So we had that for legs 3 to 9. After 9, the ship was in dry dock, and then it went back from leg 10 to 20. Leg 19 and 20 were taking instruments down, but you can see, for the most part, there was a lot of green here, which showed things are working quite well. Publications already coming out related to MAGIC. Peter Kalmus and Zhao Tejera and that group at Caltech and UCLA and JPL have several papers on this. They're looking at energy and water budgets in the boundary layer there. Let's see, Xiaoli Zhu and Pavlos Collius at McGill have a really good summary paper on that. Danny Rosenfeld and one of his students has that. Christine Hsu and a group at El Aranta and some others have looked at joint retrievals with LIDAR, radar, and so forth. David Panamel and Pat Menis and group at NASA have been doing quite a bit. I think they have another paper coming out, and they've done some really good stuff on that. So this is just here you can see if you need. And with that, that's my hint to finish up. Future plans, Magic 2 is proposed, which is another year of the same. Several times, 1 year it was accepted, and then the shipping company went out of business, so we missed that window of opportunity. We put in the proposal the next year, and Greg McFarquhar, the University of Illinois, got it, and congratulations to him. It was great. They're doing the Southern Oceans, so it's kind of a magic. It's going to be shipboard again, but they're going to put it on the Southern Oceans, making 5 round trips between Australia and Antarctica, and that looks like a fabulous deployment. So I've been talking to Greg, and hopefully they can learn use a lot of what we did from Magic to make sure they get a top-notch data set. Magic Light has been proposed. I need to go over that. Putting a set of autonomous instruments where you don't need technicians, and I think there's a lot of good data that we can get from just a nice little suite of instruments that run by themselves. We get liquid water path. We can get radiometric stuff, so we can get fluxes out of that. Cloud properties with the CML and cloud mode. We can get effective radius and so forth. I've got other plans for future marine deployments we can talk about offline if you're interested. The Magic data, like Dan said, they're not my data. I want everybody to work on it. They're freely available to all. Probably the best place is the bottom of the ARMS Magic webpage, which is here. And there's a tutorial for accessing ARM data you can look at here. It's sometimes a little challenging, or I found it that way. But call me if you have any questions, or they have a number there. Actually, it would be better for the archive. They're very good about helping that. Additional information, we have a best estimate that Tammy Toto here at Brookhaven has done for the entire deployment. The ship motion at 10 hertz, showing pitch, roll, yaw, and all this for your radars. And then we have a 1-minute resolution if you're a modeler of just where the ship was, lat and lon, every 1 minute. And then Mike Reynolds has 1-minute time series of best meteorological, where he's selected which side the wind was coming from. And you've got wind speed, temperatures, and all this. The bulk aerodynamic fluxes, which is a wonderful data set. And then he also has leg reports of pictures of atmospheric profiles and so forth for each leg. And then Micah, like I said, has put the ECMWF data into the ARM archive. Websites, there's 3 different websites. This is one I have that has an overview like this. It's a little dated, a lot of other information. ARM's website on it, and Mike Reynolds on his website, webpage has a very good site on that. So I also have files of when the legs officially started and stopped. We'll try to keep it consistent here. Instrument status tables of all the radio sun launches and README documents that I'm trying to work on so that you don't come in uninitiated. You can kind of read that and see what you need, which things worked well, how to do that, and so forth. So with that, thank you very much, and I will take any questions.